When analyzing binary clinical outcomes or bounded count data, applying classical ordinary least squares regression guarantees structural failure. The math physically breaks down. The first point of failure is variance. OLS assumes homoscedasticity, a constant variance across all predictions. But for binary data, variance is inherently tied to the mean. A probability near 0 or 1 has a much tighter variance than a probability near 50%. This chart shows the second failure, impossible predictions. Plotting a standard linear regression line through binary outcomes extends past the 100% ceiling and 0% floor. OLS readily outputs a negative probability of death, or a 120% chance of recovery. Because of these mathematical violations, OLS cannot reliably synthesize survival data or model rare clinical events. The resulting estimates are structurally invalid. To model clinical events accurately, the statistical framework must respect the natural boundaries of the data, rather than forcing events into an invalid linear shape. The Generalized Linear Model, or GLM, solves this by replacing the rigid OLS structure with three flexible modular components: the random component, the systematic component, and the link function. The random component specifies the probability distribution from the exponential family, like binomial or Poisson, that actually matches the data. The systematic component remains the standard linear predictor combination of our variables. The link function is the mechanical engine. It maps bounded responses onto an unbounded scale, where the linear systematic component operates safely. You compute math on this infinite link scale, back-transform probabilities to the bounded original scale, and evaluate effect sizes on the comparative scale. In R, this architecture is implemented using the base GLM function, specifying the formula, the data, and a family argument, like binomial. Instead of relying on R², the model's fit is evaluated via deviance and the Akaike information criterion. Understanding this exact mathematical mapping is the prerequisite for scaling up from single, isolated studies to multi-center trials and large-scale meta-analyses. Multi-center clinical trials introduce the statistical threat of clustered or nested data structures. Patients are nested within specific hospital sites, and those sites operate under distinct protocols and populations. Ignoring this nesting violates the core statistical assumption of independence. Treating clustered patients as entirely independent artificially shrinks standard errors and drastically drives up type 1 error rates. The mixed effects framework resolves this. Fixed effects represent constant parameters. Random effects act as safety nets for level 2 clusters, adjusting the baseline for deviations. This creates shrinkage. The random effect pulls unstable estimates from small clusters back toward the global mean. By combining these elements, the generalized linear mixed model structure takes shape. The link function of the expectation equals the fixed effects plus the random effect vector for the specific cluster. Lacking closed-form solutions, GLMMs rely on intense numerical approximation routines, specifically adaptive Gauss-Hermite quadrature, to integrate out the random effects and solve the likelihood equations. Random effects function as structural necessities, mathematically governing exactly how much we should trust data originating from sparsely populated trial arms. Traditional two-stage meta-analysis frameworks rely heavily on normal approximations. For rare events, where counts are extremely low, these approximations fail completely. When legacy software encounters a zero-event cell, the log odds calculation divides by 0 and errors out. To force the math to work, analysts historically applied a continuity correction, adding an arbitrary 0.5 to the empty cells. Using continuity corrections is the statistical equivalent of fabricating patient data simply to appease outdated software limitations. The rigorous alternative is the one-stage exact GLMM. By modeling the raw cell counts directly and treating individual patients as level 1 units nested within level 2 trials, it preserves the true exact data likelihood. This exact modeling supports 3 distinct paradigms: fixed intercepts with fixed treatment effects, random intercepts with fixed treatment effects, and fully specified random intercepts with random treatment effects. In R, these models are estimated using the GLMER function and can be passed directly into the RMA.GLMM function from the metaphor package to generate exact, assumption-free forest plots. By modeling the raw counts directly in a single stage, biostatisticians eliminate mathematically invalid approximations and preserve the absolute integrity of rare event trial data. Applying these models to time-to-event data requires an additional dimension. Standard proportions and odds ratios completely fail here because they ignore event timing and cannot handle patients who are right-censored. Using rigid time definitions in survival models introduces immortal time bias. This error artificially assigns unearned at-risk survival time to an exposed retreated group. We can observe this bias in historical studies claiming that winning an Academy Award extends an actor's lifespan. Winning an Oscar is an observational milestone that divides a subject's timeline. The actor had to survive long enough to win the award, but naive models credited those pre-award years of survival entirely to the Oscar winner category. To correct this, the index date must shift from initial observation to the actual time of the milestone. The subject's timeline is partitioned into multiple rows using time-varying covariates, easily executed with functions like surfsplit or tmerge in R. This chart shows the consequences of failing to apply this time-dependent partitioning. Looking at the top left panel, the naive Cox method generates severely biased hazard ratios that falsely suggest protective or exaggerated effects, while the time-dependent models correct the coverage rates. The strict rule is this: any person time accumulated before a treatment or milestone is officially achieved must be mathematically assigned to the unexposed control group. Survival analysis is structurally invalid if it fails to align the exact timing of state transitions with properly partitioned person time intervals. Once follow-up time is accurately partitioned into discrete intervals, a critical mathematical equivalence emerges. A piecewise exponential survival model becomes perfectly mathematically identical to a mixed Poisson regression. The practical barrier to deploying this equivalence is that biostatisticians reviewing published literature rarely have access to the raw interval data required to build the Poisson model. The Guyot iterative digitization algorithm resolves this. It reverse engineers published aggregate Kaplan-Meier curves back into usable pseudo-individual patient data. With the pseudo data generated, we can map survival directly into the Poisson GLMM architecture. On the left side of the equation, we model the expected count of the number of deaths or events. The first input is the offset term. This is the log of the exact person time exposure derived from the partitioned intervals, ensuring we only model rates, not absolute counts. Next, we add the baseline hazard for the specific interval, plus our fixed effect measuring the treatment impact. Finally, we include the trial-level random effect, the mathematical safety net that adjusts the baseline for clustering across multiple published studies. You execute this in R using the GLMM2MB package, declaring the Poisson family, binding the pseudo data, and strictly defining the offset argument for the partition time. By treating survival data through the unified architecture of the Generalized Linear Mixed Model, biostatisticians eliminate data fabrication hacks, control for trial-level clustering with exact precision, and achieve perfectly mathematically rigorous multi-level survival synthesis.